All right, well, now we are ready, I think, to finish up the topic of the ecological approach to perception. So this should be the last video in that series. And we are talking here, I have labeled this section of the notes looming, but one thing I want to emphasize is that this is also under the kind of umbrella of local optic flow. So in the last video, I spent a lot of time talking about the patterns that are uh, uh, present in global optic flow that can specify things like depth layout and heading direction, approach and retreat. And then, of course, the global flow versus local flow distinction was all about self-motion versus object motion. But I mentioned a few things about local flow, such as the idea is that if an object is coming at you, like someone throws a ball at you, you're going to have a focus of expansion localized within the contours of the object itself. On the other hand, if someone has thrown the ball to one side of you, then in that case, there will not be a focus of expansion, but rather you're going to see something that we'll call lateral flow or something like that, laminar flow, maybe to capture the idea that all the flow vectors are pointing in one direction rather than all radiating outward from a central point. But let's assume that the object is, in fact, coming directly at you. It's going to hit you, right? And this is what we're calling looming, right? If you understand the idea is that if someone is looming over you, that means they're standing over you, right? Well, in this case, the idea is that an object that's getting closer and closer to you is also generating what we call an optical looming effect, because as it gets closer and closer, it gets larger in your field of view, right? We learned all about that when it's talking about size and distance perception and size constancy and all of that, right? So in this situation, again, we have this looming effect happening that this object is coming at you. And in order to fully understand what's happening here perceptually, and what kind of information is available to the person perceiving the object coming at you, we need to do some further, deeper analysis of optic flow here. This is where I want you to buckle up because we're going to have some fun with math today. We're going to do some, not just some algebra, we're going to do geometry, we're going to do some trigonometry maybe, we're going to do some calculus. That's fun, right? So you never expected to have any of that in this course or maybe in any psychology class. But don't worry, just as I said when we covered a little bit of math in psychophysics, I'm not testing you on mathematics in this class, but we're going to use the mathematics as a tool to see how we can find information, right? Now, these two charts here are probably a little confusing to understand at first pass. And I have another video, so actually, I guess I lied a little bit because I said this would be our last video under the ecological approach, except I do have another video. I made it actually a couple of years ago, and I'm going to go ahead and upload it here somewhere in the module, where I'm using, like on my iPad, I'm using the whiteboard feature of Zoom to draw these charts out one by one at a time, bit by bit, so I can maybe explain a little bit better than what you can get from this. And I continue to go through all the math that I'm just talking about in that video as well. So you can watch that too, maybe for a slightly slower, more detailed explanation for what this is all about. But what I'm trying to depict here is the optical projection of an approaching surface, right? So what we see here on the left, this big vertical line on the left here is an optical projection surface. And maybe this is that imaginary sphere we've talked about, right? That could be what we can use here as our kind of working model of what's happening. So information in the world is being projected onto that imaginary sphere centered around the point of observation. And we want to understand what kind of information is present in that optical projection. So we have to do projective geometry. That's what this is really trying to depict here. is some projective geometry. What is projective geometry? Well, the idea is that we have something happening in the world, but we want to project it onto a two-dimensional surface, such as the surface of that sphere, or when you're projecting on something onto a projector, like using a projector on a screen, right? That's a projection as well. There's some geometry for that. So what we have here is an object in the world, and that's what this on the far right-hand side is, this vertical line, right? And there are now sight lines or rays. This is a ray diagram, and so we're going to have these rays coming from the top. That's what this diagonal pixelated line is, as well as the bottom, which is this one long horizontal line, is really just a sight line from the bottom of the object. So we're just looking at this object as if it's maybe just a single, if you look at the camera point here, single object seen from the side that's moving towards somebody. So I'm going to use my, I get some props here. I'm going to use my little elephant statue, and here's an object that is moving towards the elephant statue. That's what I'm trying to depict as a side-on view here. Is this flat object that's going to come and hit our elephant in the face. And the projection, the optical projection that we're depicting here is what kind of information would be available for the elephant if it wanted to know something about what's happening here. So what we have here is we have not just the object here at this first position on the far right-hand side, but as it approaches the elephant, I guess, right? Then it's at a new position at some point in time later. It's getting closer. So that's we're marching it now further and further to the left in the diagram. So it's at point 1, and then it's at point 2, 3, 4, 5, 6, 7 steps forward, right? And so as this object is moving forward over some period of time, it's going to get closer and closer, and we have marked out its advancing position at 7 points in space. And for each one of those, we have drawn through the projection, focal point of the projection. And that's what this sort of nodal point is right here in the diagram. All of the sight lines are projected through the nodal point or the focal point in the projector. And then all of that is now projected onto our projection surface on the far left-hand side. That is the large vertical line there. And so what we have here is essentially the relative position of the bottom of our approaching object, which stays fixed the way I have drawn it, but the top of our projected object is now getting is moving, right? And it's moving downward on that projection surface because, of course, just like the lens in the eye, this projection here is going to invert the image, right? So that's what's happening. We've inverted the image here. But one of the things that we want to notice here is what are the visual angles, right? And how do those visual angles change over time? And that is optic flow, as I described in the previous video, right? And so we have our initial visual angle, and it's going to increase by some amount, and we can see the change in the spacing between these lines here in the optical projection. And what we're going to see is that the spacing between these changing positions, changing angles, is ever increasingly large, right? So that's important because what's happening here is that this object is actually traveling at constant velocity. Now, how do we know it's traveling at constant velocity? Well, imagine that as we look at this, the change in the position of this thing over time, as it steps forward to 1, 2, 3, 4, 5, 6, 7 points, we're sampling it at a regular time interval, like once every second. And so every second, we're going to get an update. Where is this object at, right? And how far has it traveled? And it's traveled the same distance every time we check up on it, right? And that means that if we check it every second and it's always traveled the same distance once every second, that means it's traveling at some constant, number of feet per second, let's say. And therefore, that's a specific constant velocity of an approach. It's traveling at 7 feet per second, let's just say, right? So what does that mean in terms of the optical information? This object that's coming at you at a constant velocity is actually generating an optical pattern that is not just getting larger in your field of view, which should obviously be true, I hope, but it's getting larger at a specific rate, right? And the rate at which it's getting larger is accelerating over time, meaning that it's getting larger, and then it's getting really large, and then it's getting really large, and then it's getting really super large in your field of view, right? That's the looming effect that I'm talking about. And the idea is that when the object is coming at you at constant velocity, we're going to get not a constant velocity of the image expansion, but we're actually going to get an accelerating. Acceleration means that we're changing velocity, right? So constant velocity would mean no acceleration. And that's what's happening in the world as the object is approaching our elephant in my demonstration earlier. But from the elephant's perspective, the projected image of that object into an optical pattern is accelerating in its size, right? It's growing at an exponential rate. And that is what creates the effect of looming, which is kind of a psychological effect, if you think of it that way. Because as I said, when someone is looming over you, it gives you that impression that, like, hey, back up, right? So the idea is you get that same effect here, is that when something is looming at you because someone has thrown a ball right at your face, obviously that's going to create the same psychological response. You're going to want to put your hands up and say, no, it's coming at my face. I need to duck, or I want to block it or catch it or something, right? And what is the information for that? The information is the presence of the accelerating image expansion in the first place, right? So when we experience an accelerating image expansion, that turns out to have a unique correspondence, again, a one-to-one mapping to an object approaching at constant velocity. Now, what's also important about an object approaching at constant velocity means that it's not only not accelerating, it's not slowing down either. And so if something's coming at you and it's not slowing down, then that's actually important, something important you'd want to know, right? Because it means it's going to hit you. And so, yeah, it should create the psychological effect of putting up your hands or ducking or something along those lines, right? And so what gives us the information that it's not slowing down? The accelerating rate of image expansion, right? And that's what this diagram on the top half of the slide here is trying to communicate. Now, on the bottom, we've depicted something else. In this case, notice how the spacing between the object's positions, I think I got 7 again here. 1, 2, 3, 4, 5, 6, 7, 8, I guess. Now the spacing between them is getting smaller with each step forward, right? And so what happens if, in 1 second it travels a certain distance, but in the next second it travels a little less distance, and in the next second after that it travels even less distance than that. That is the literal definition of slowing down, right? Is that it's traveling less distance with every second. And what we see is that the optical projection of that does not result in that same sort of exponential increase in the projected image, but rather it results in simply just a smaller, more linear increase. That is more constant, fixed increase in the image expansion. And so that's a very drastically different appearance here. When something is coming at you, it's still going to expand in your field of view because it is getting closer, but because it's decelerating, that's going to keep the rate of image expansion or optical expansion to be much more of a smaller, more fixed, constant rate of increase as opposed to the exponential rate of increase when it's coming at you without stopping. So if something is going to stop, you're going to have a very different kind of optical pattern, which is the bottom, compared to if it's not stopping and it's going to hit you. And so the top half is the looming effect that signals get out of the way. The bottom half is a different effect that has a different optical pattern, a different rate of optical expansion. And that signals something else, such as maybe, oh, it's going to stop short before it ever collides with me. Where is this useful? Well, it actually might be useful. This is more of a global flow situation rather than a local flow. But imagine when you're driving a car and you're pulling up to a stoplight, and there's a car in front of you that's already stopped at the stoplight, and you need to come to a stop without colliding into the rear end of the car in front of you. So you're going to start hitting the brake pedal, and that's going to slow your car down. And that means every second you're traveling less and less distance. But you're still, of course, going forward, and you're still getting closer to that car. And the rear end of that car is still going to expand in your field of view, but it's going to expand at that more constant rate as opposed to an accelerating rate. So if you've ever been in a situation where you have started to hit your brakes and you realize that you're not slowing down sufficiently, you're going to get a looming effect. You're going to realize that the rear end of the car in front of you is still accelerating it's increasing at an accelerating rate. And that usually creates that response of, oh crap, I got to hit the brakes a little bit harder, or I'm going to hit this guy, right? And so we can control our rate of deceleration when driving by detecting when we have an accelerating rate of image expansion, which would specify insufficient braking, or a more constant rate of image expansion, which may specify sufficient braking, right? Now, it's a little more complicated than that when it comes to knowing exactly what's the just right amount of braking, but for a simplified case here, when it talks about insufficient versus sufficient braking, I think we can cover it here, right? But now let's, so that's, I kind of have some of the same stuff over here, right? So again, this is our constant deceleration, right? So that means constant decreasing velocity. But that constant deceleration results in a constant optical expansion, specifying that's going to stop, and therefore we don't have to worry. But here, the looming effect is when we have the constant velocity of approach resulting in the exponential increase in the optical expansion rate. And that's going to tell us it's going to hit, right? Now, our next question that we want to know is when, right? Because that's important. And we want to know when it's going to hit because we want to be able to put our hands up at just the right time. Or maybe I want to duck or do something else. But the idea is that in order for me to engage in some kind of what I would call interceptive action here, and we already know that people can engage in interceptive actions very, very well. If you can catch, if you can play dodgeball, if you can, I don't know, if you can drive a car, then you are capable of engaging in interceptive actions to some degree, right? So that means that we must have some kind of perceptual information about timing here, right? And that timing is what we're going to call time to contact. Okay? So if it's coming at me, what is its current time to contact? That just means time until it hits me, right? So what is the time left until it hits me? Is it 5 seconds? Well, okay. Then if I know I got 5 seconds, is enough time to get my hand up there, right? So the next question is, how do we know the time to contact? Or how can we perceive time to contact? Is there any information about time to contact? Because we can think of it in a couple of ways. One way to think about time to contact is to think about possibly doing a little bit of mental mathematics, right? So let's think about it. Let's say that this object is approaching at a rate of 10 meters per second, right? I'm just picking that number for mathematical convenience. If the object is coming at me at the rate of 10 meters per second, and it's 20 meters away, what do I know? I know it's going to hit me in 2 seconds, right? Because if it takes 1 second for this object to travel 10 meters and it's currently 20 meters away, then obviously it's going to need 2 seconds in order to collide with me, right? So my time to contact will be 2 seconds. But in order to do that kind of mathematics in my head, I would need to be able to simultaneously perceive the exact distance of the object at 20 meters, as well as the exact velocity of the object at 10 meters per second. And it's not entirely clear that humans or any other animal that might be capable of interceptive action. And of course, there are other animals that do this, right? Dogs, for example, can catch a ball and whatever, right? But anyway, it's not entirely clear that humans or any other animal are capable of that kind of precise performance, right? Of exactly judging the current distance of an object at exactly 20 meters away, and especially the more demanding task of exactly judging the velocity of this object at precisely 10 meters per second. So if we can't do those two things very well, that is judge distance and judge velocity, maybe we cannot judge time to contact very accurately. Well, we're going to wait till the end because there's an experiment by Jim Todd, we're going to talk about that experiment at the end, and we're going to ask that question: can people judge time to contact accurately? But let's consider an alternative to my little thought experiment here about doing all of this kind of implicit mental math to first judge speed and distance and then compute time to contact. What if there was a way to directly perceive time to contact information, right? That is, without performing other kinds of perceptual judgments and doing some form of perceptual inference or other kind of computational process. What if we could just directly perceive the time to contact? And this is where we want to do the math that I talked about at the beginning of the video. Is it possible that there's an optical variable that has a unique or one-to-one correspondence to the time to contact? Well, let's do an analysis here. So here again is our diagram of the approaching object projected into optical patterns. And I have all of our variables defined here at the top. So capital R is the length of that one side of the triangle, right? But that's actually the size of our object here. Why is it called R? Because we're actually going to think of it as a radius, but don't worry about why. It's just that's the size of our object. Now it's approaching at constant velocity v. So I have the v with the arrow there, showing that it's moving from right to left, right? So it's got that velocity vector v. It's at a distance z. And we're going to use z for distance because we're going to think of it in terms of the Cartesian XYZ coordinate scheme. And z is usually the depth dimension in that scheme, right? Now, one thing I want to point out is that the z is the distance from the projection point, which is that intersection here of these two triangles to the bottom of our object R, right? So that's the distance. And so essentially what I have here is I have the lengths of two sides of that triangle, right? And it's a right triangle. Let's point that out. So if you remember from trigonometry, a right triangle, you're going to have a 90-degree angle there. And so one side is R and the other side is Z. We don't know the length of the hypotenuse, but if we know R and Z, we can use the Pythagorean theorem to get the hypotenuse, but we're not going to have to worry about that right now. Now, meanwhile, there's another smaller triangle over here on the left side, right? And that's our optical projection. So what we know is that the object is now expanding in the optical pattern. So we're going to have an optical velocity vector that's also a v. But one thing I want to point out is that I'm using a small or lowercase v instead of the uppercase v that we had on the right. And so we're going to use a convention here, and I want you to make a note of it. When we use uppercase letters, we are describing a state of affairs in the world, that is some physical measurement from the world. When we use lowercase letters, we're describing optical variables. And so the idea is that we want to make sure that we are maintaining a distinction between an optical variable, such as the optical expansion rate, lowercase v, versus the real world variable, and that's the object's velocity in the world, uppercase v, right? And the same applies to our R, right? The object's actual size in the world is R, capital R, but the projected image size or optical size is going to be that lowercase r. And so once again, we have a little right triangle here that has two sides and a hypotenuse. And one side of that, the shorter side of the triangle, is that lowercase r for its projected optical size. And the longer side is not z, but it's 1. So where in the world did we get the 1? Well, because this is the optical projection surface here, we get to define our optical projection, and we're going to define that as having a unit distance, right? And a unit distance simply just means that the optical system defines its own units, right? And everything is scaled in units relative to the optics of our elephant, let's just say, for example, right? So we're going to call it 1, and that sets the units of the optical projection. So we have now, again, an object of size r at a distance z approaching at velocity v, and in an optical projection, it has an image size lowercase small r and an image expansion rate small v. But I want to also point out that we have these t in parentheses, right? So t stands for time, because what we need to also realize is that 3 out of these 5 variables can change over time, right? Constant velocity in the world does not have a time index because it's never changing its velocity. It's not slowing down, it's not speeding up, so that's never changing. So at time 1, at time 2, at time 3, v is always the same. The object has a constant size r. It's not shrinking, it's not growing, right? So at time 1, time 2, time 3, r is always going to be the same. But the distance z is changing, right? We saw that on the previous slides, right? Here, right? Over time, the object gets closer and closer and closer. So that means that z at time 1 is greater than the z at time 2, which is greater than the z at time 3. So z is getting smaller and smaller. So we need to have a time index on that. Likewise, since the object is getting bigger in our field of view, its image size or optical size is growing. So we need a time index on the small r. And remember what I said about the looming effect. The rate at which it expands is exponentially increasing. It's an accelerating image expansion rate. So that means that even the small velocity, small v in the optical projection also needs a time index, because the optical expansion rate will change over time. It doesn't map directly to the constant velocity of the object in the world. So let's remember some geometry. And these two triangles, the small one on the left and the larger one on the right, are similar triangles. That means the interior angle there, where the two triangles and their tips point, is the same angle. And if they are similar triangles, that means that the ratios of their sides will be equal to each other. So if I take the ratio of our optical triangle on the left, and as one side has a value of 1 and the other side has a value of small r, then 1 over small r is a ratio of those two sides. And then the same ratio for the larger triangle, z over r, capital R, that ratio should be equal to the 1 over small r, right? So that's just a principle from geometry, that when we have similar triangles, the ratios of their sides will be identical because their internal angles are all identical. So we're going to start with that small fact, right? 1 over r is equal to z over r. So what are we going to do next? Well, here's where we're going to do calculus. So if you have never had calculus, don't worry, just go with it. But this is the kind of stuff that you should get in just basically an intro survey of calculus. It's called the quotient rule, right? So what we're going to do is we're going to take the derivative of the left-hand side of that equation, 1 over small r, and we're going to also take the derivative of the right-hand side of this equation, z over capital R. And if those two ratios are equal to each other, then their derivatives are also equal to each other, right? So so if 1 over small r is equal to z over r, then the derivative of 1 over small r is equal to the derivative of z over capital R. What's a derivative? Well, a simple way to get this across, and maybe we don't need to worry about it too much, is that in calculus, the derivative measures the rate of change in something, right? How does something change over time? And that's what we want to know, is how is that ratio 1 over small r changing over time? Because there is a time index in that thing, so it does change, right? And the same for z over r, that changes over time too. And so what's the rate of change on both sides of the equation? So in order to take the quotient rule, if I remember this right, I'm looking right at my slide, so I should remember. The first step in the quotient rule, so this is what I have, d over dt of that 1 over small r. That's what I want to know the answer to. D over dt means I want to take the time derivative with respect to time as measured by the variable t. So the first step in the quotient rule is to take the denominator times the derivative of the numerator. So the denominator is that small r of t, and so that's what our first part of that solution shows, times the derivative of the numerator. Well, another simple little principle from calculus is that the derivative of a constant is always 0, because the derivative measures something that's changing. And if you are trying to take the derivative of something that's constant, that means it's never changing. So the derivative is 0. And so small r times 0 is our first little step here, right? And that obviously is going to disappear because anything times 0 will be 0. Now, the next step of the quotient rule is to take the numerator, which is 1, and multiply that times the derivative of the denominator of small r. And our final step of the quotient rule to finish the formula is square the denominator. So we're going to have small r squared. And that's the quotient rule, right? Is to take the derivative of a fraction, which is a quotient. We have to apply the quotient rule. And that rule says denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared. So we have that r times 0 minus 1 times the derivative of r divided by r squared. Now we're going to simplify this a little bit. How can we simplify it? Well, as I said, r times 0 is just going to disappear, right? Because of that 0. So we're going to be left with the minus 1 times the derivative of r, right? The 1 is a little bit redundant at this point, right? Because of the identity issue of multiplication. So 1 times something is just something. What is that something? The derivative of r. What's the derivative of r? Well, the r is the image expansion rate, or sorry, image size, right? The optical size r. And because that's changing over time, its rate of change is its optical expansion rate, small v. So the derivative of the small r is in fact that small v of t. So now I have the solution to taking the derivative of the left-hand side of our original equation, 1 over small r, and that is v, small v, over small r squared. All right, that's what we have left. That's just applying the quotient rule. Now on the bottom, I am taking the derivative of the right-hand side. And again, I am applying the quotient rule. And the quotient rule is going to give us, now I think I've simplified the process just a little bit, but it's going to give us a very similar answer, right? It's going to give us capital V over capital R. So there we have the derivative of the right-hand side. So if it was true that 1 over small r is equal to z over r, then it should also be true that small v over small r squared is equal to capital V over capital R, right? And all we have to do now is we're going to invert those two ratios. Why? Because it's going to make our lives a little bit easier. And it's a perfectly valid legal thing to do in mathematics. So if I say that small v over small r squared is equal to v over r, then it's also equally true that if I just invert both sides of the equation, this new equality holds, right? So that would mean that small r squared over small v is equal to capital R over capital V. And that's what I have written on the very bottom of this slide, is that the small r squared over the small v is equal to the capital R over capital V. So we have done some fancy math, right? We found an equality by similar triangles. We differentiated the left-hand side and we differentiated the right-hand side, and we inverted those results to get a new equality, which is what I have at the very bottom. And I have got that here as well, right? So I've got that same inversion. So we had the result small v over small r squared equals v over r. We invert it, and we have the solution, the result I want, which is r small r squared over small v equals r over v. If you followed all of that, and I apologize, there was a lot of repeating variable names over and over again. And some of the derivation I kind of just glossed over because, like I said, I'm not really trying to test you on the math here. If you know the quotient rule, you can try it for yourself if you want. But now we want to do something else. We're going to just take this a little step further, and here's where we're going to do a little bit of algebra. What I want to do is I want to go back. Let's go back to our original equality. I went back 2 slides here. 1 over small r equals z over r. What if I were to solve this equation for r, right? So in order to solve this equation for r, one thing I could do is I could invert here, and that would mean that I would be left with small r over 1, which just simplifies to small r, is equal to r over z, right? And then to further simplify, I would have to multiply both sides by z. And so I would end up with the capital R equals z times small r. And that's what I have right here, right? By solving that original equality for our capital R, we know that r is equal to capital Z times the small r, right? So what I want to do is I want to take this new quantity, z times r, and I want to substitute that in this equation above where we have the capital R in the numerator of that r over v ratio. So that's what I have on the very next slide here. So now I have a new ratio. I've got the r squared, small r squared over small v. It's now equal to the z times r, or small r, over v. Now, what else do we want to do? And why did we make this move in the first place? Well, this allows us to do something. What if I now divide both sides of this equation by small r? What that's going to do is on the left-hand side, it allows me to get rid of that square, right? And on the right-hand side, it allows me to just get rid of the small r entirely. So our new thing, our new equality, and now that we've divided both sides by small r, is it's going to be small r over small v on the left-hand side, and it's going to be z over v on the right-hand side. We've solved our problem. Now, you might be completely lost here, but let's think about it. Remember what I said earlier. If our object is traveling at 10 meters per second, and it's 20 meters away, how long until it hits me? 2 seconds. Well, let's plug those numbers into this formula here, z and v, right? Z is the distance, 20. And so look at my little blue box here on the side where I got m over s, and that's the units of this of that fraction. Z is measured in meters, and so that might be 20, right? Velocity is measured in meters per second, so the ratio here is meters over meters per second. Those are the units of the z over v fraction. So if the distance z is 20 and the velocity v is 10 meters per second, that 20 divided by 10 meters per second is just going to give us 2, right? And that's going to give us our 2 seconds. So the z over v ratio is, in fact, the mental math that I suggested we might be able to do if we happen to know z and if we happen to know v, right? So if I am able to perceive the distance z and perceive the velocity v, I could calculate with my own brain the time to contact. But what I already said and began this whole section with was the raising doubt about whether we can do this. Can we really perceive the distance and the velocity accurately and compute the time to contact ourselves? And the answer is probably not. But what if there's optical information that uniquely corresponds to the time to contact? Well, look at the left-hand side of our equation. Small r over small v are both optical variables. Remember when I said we wanted to make a distinction between the lowercase variables that refer to optical variables versus the uppercase variables that refer to things happening in the world. And what I have now demonstrated is that the optical variable defined by the ratio of r, small r over small v is equal, and that's a very important equal sign, to the z over v, which is the time to contact in the world. So this equation proves that there is optical information about the time to contact. So what this would now mean is that if a perceiving agent, like maybe my elephant that has something that's going to come and hit it in the face here, is capable of detecting, if the visual system of our elephant is capable of detecting the small r over small v ratio, it is then capable of perceiving time to contact directly. And that kind of perception of time to contact would not require any additional steps of cognitive inference, right? It would not require that we have to compute anything because the time to contact information is given directly by the small r over small v ratio. And for simplicity, we're going to stop calling it small r over small v, and we're just going to give it a name. And we're going to give it the Greek letter tau as its name. And so the claim here is that this ratio, small r over small v, otherwise known as tau, which could be described in what I've written on the slide here as the ratio of the image size divided by the image expansion rate. That's what r is the image size and v is the image expansion rate. The ratio of those two things has a unique one-to-one correspondence to the time to contact, and therefore it specifies time to contact, and therefore tau is in principle information about time to contact, assuming constant velocity, but you already know that, I hope. So what we would say here is that we have yet another optical variable in an optical pattern that could specify something that is important and meaningful without any need of additional cognitive steps like inference and so forth. So again, when I started talking about the ecological approach, I was suggesting there's all of this in the sensation-mediated view. There's this assumption of a poverty of stimulus, right? And the whole goal of all of the stuff that we've worked through in this set of notes is to show that there really is not a poverty of stimulus, right? There's in fact a very enriched stimulus, but only if we step outside of the retinal image and we start looking at these optical patterns, the optic array, the texture gradients, the optic flow field with the flow gradients and the focus of expansion and the local and global flow. And the inflow and the outflow, and now also the tau variable could also be part of all of that. And we're going to call it a higher ordered variable because it's a slightly more complex one than simply just detecting the focus of expansion or something like that, or the presence of inflow and outflow, because it's a ratio of two other optical variables, right? And that makes it more higher ordered. But the claim and the hypothesis here from a psychological perspective is that this could now be used as information. But if we remember from our perturbation experiment stuff at the end of the perceptual constancy notes, it's not enough to simply demonstrate that the information is there. That's step one. Step two is to then perturb the information to see if perturbations of that information directly result in changes to someone's perceptual judgments. And when I describe the moving room experiments, that's a perturbation of the inflow and the outflow. And that results in an appropriate perturbation of someone's perceptual judgment as measured by their changes in posture and stance. But here what we need to do is we need to now perturb the tau variable and demonstrate that changes in the tau variable directly affect someone's judgment of time to contact in ways that would not be explained by their ability to perceive velocity or distance and do that kind of mental mathematics that I suggested was not likely to be possible. That's where we want to come to Jim Todd's experiment way back in 1981. The paper was titled here, Visual Information About Moving Objects. This little diagram here is meant to be kind of a simulation of the kind of display that Todd created to simulate approaching surfaces. So we have these little, let's see, 8 dots, right, that are configured in roughly a square pattern. And the arrows are on the outside of the flow vectors depicting the idea that it's coming at you. So imagine you're looking at a computer screen and you're going to see this little rectangle or square defined by 8 dots. And it is coming at you in the screen as if it's going to collide with you. Right? In fact, let me try to simulate that here. I have my little coaster and it's square. And I'm going to move it towards the camera, and it will, your goal group is to determine when it's going to hit the camera, which would be equivalent to your eyes in a way, right? So here we go, well, when will it hit, right? But instead of a camera, you're now seated at a computer looking at a computer screen, and you have 2 objects that are approaching like this, right? And we see one on the left and one on the right. One on the left is obviously a little bigger, right? Your task is to not judge time to contact in absolute terms, like say 3 seconds, 4 seconds, whatever, but simply just to determine which one of these 2 approaching surfaces is going to hit first. So we have a simulation now of 2 objects coming at you at the same time. And then at some point before they actually hit the screen, metaphorically speaking, they're going to disappear, right? So he just cuts the display off. And so the question now is, at the last time you saw these 2 things, what was their, on the current trajectory they were on, which one of those is going to hit the screen first? And you have to just make a judgment. And the reason that I have it kind of drawn this way so that one square is large and one is small, the idea is that one of the things that Jim Todd did in this experiment to provide some sort of experimental control over this was that he randomly varied things like the size of these approaching objects as well as the starting distance, right? So if it's going to kind of be a simulation of an object that's approaching the screen, then it has to start at some simulated distance behind the screen. And so he randomly varies that, but he also then varies their rate of approach. So it could be the case that sometimes an object is approaching very rapidly at a very high velocity, but it starts so far away that it's actually not going to be the thing that hits first. There might be another object that's approaching more slowly, but it is much closer up, so it may actually have a shorter time to contact. And the point of that kind of manipulation is to show that if people are paying more attention to something like simply just the approach velocity, then they're going to judge the thing that is moving faster as hitting first, even though that's not always true. And so if they're relying simply on approach velocity, that means they're going to make mistakes, and they're going to incorrectly judge the fast-moving object as hitting first when it's not true. Or sometimes people might be judging the thing that's closer as going to hit first. So sometimes there might be an object that's close and then another object that's farther away. But maybe it's the case now that the further object is moving so fast that it will catch up and pass up the moving object. So sometimes the closest object will hit first, and sometimes it's the farthest object will hit first. Sometimes it's the fastest object that will hit first, and sometimes it's the slowest object that hits first, right? So the idea is that if a subject is purely relying on their ability to judge the simulated distance of the object or the simulated velocity of the object, those 2 pieces of information are by themselves irrelevant to the task in a way, right? And if someone relies on those kinds of things, they're going to make a lot of errors. So the question is, did people make a lot of errors? And if they did, that would suggest that they're not really judging time to contact, but rather they're just trying to judge the speed or the distance. But as it turns out, here I have the same image, but now some new text here. As it turns out, the participants in this experiment did not make a lot of errors. In fact, they demonstrated greater than 90% accuracy at judging which of the two objects we're going to hit first here. So again, if I say that it's, the size of the object was not informative, the distance was not informative, the expansion rate or velocity was not informative, the only way that someone could be accurate consistently at this task is if they were capable of detecting the image size over image expansion rate variable directly, that is the tau variable directly. And even when the differences in the relative time to contact between the two surfaces was as narrow as 100 milliseconds, that's just a tenth of a second, right? A fraction of a second, people could still tell that difference and correctly judge at greater than 90% levels, right? So that shows a remarkable degree of perceptual sensitivity to the time to contact information. So that suggests that I guess that's our last slide, sorry. This suggests that, yeah, right, that in order to explain the high degree of performance here, the high degree of sensitivity to time to contact information, people must be relying on the tau variable and not trying to rely on speed or size or distance, right? So that's our conclusion, right? That we have done this many steps in the process of demonstrating what the information is, right? That the tau variable is there that specifies time to contact, and that we have now demonstrated in a psychological experiment with people that people are actually sensitive to that information and use it to judge time to contact correctly. So we have the informational analysis. That's all of the math and geometry that we did. And then, of course, there's the perceptual research with actual live human beings to show that, yes, in fact, they are sensitive to it. Those two parts are really important. So anyway, as I had mentioned at the beginning of this video, I have another version of this where I use kind of the virtual whiteboard function of Zoom to draw out these steps bit by bit, which possibly makes some of the diagrams and the drawings and the math slightly more clear. So I'm going to have now two different videos that give you the same thing in two different ways. So anyway, that is now the end of the topic of the ecological approach to visual perception.